In this tutorial we're going to look at electrophilic addition reactions to alkenes, and we'll take ethene as our archetypal example of an alkene and how they behave. So first of all, to understand how they behave, let's look at the carbon-carbon double bonds, and this of course is made of two different types of bonds, where we have the first bond, the single bond, which we call a sigma bond, occupying the space between the two atoms. And then we have the second bond making up the double bond, which occupies a space above and below the sigma bond. This is the pi bond, or the double bond, the second part of it. So there's important things to understand about the pi bond. This gives us a big concentration of negative charge in this area of the molecule, and that of course means that what will be attracted to it will be anything that has a positive charge or a concentration of positive charge. And what we're talking about here are what we call electrophiles, which we are going to represent by the symbol E+. So let's look at the general mechanism. We'll start with ethene as our alkene, and we'll take our electrophile here as being any molecule where we have an uneven charge distribution, with the E being slightly positive, delta positive. So what happens here is that as this approaches the pi bond, the electrons from the pi bond look to make a bond with the electrophilic part of the molecule, and of course this means that the single bond here, the molecule must break, and the two electrons from that bond attaching themselves onto Y. And if we draw that as has happened at that stage, we find that we have bonded this carbon onto the electrophile, leaving the second carbon minus an electron and having a positive ion, and the Y part of the reagent molecule now has a negative charge. We call this intermediate a carbocation, cations being positively charged in carbo because it's on the carbon, and this is an intermediate. Doesn't really exist, it's a stage it goes through, or exists very briefly. And next step might seem a bit obvious. This negative ion will then be attracted to this positively charged carbocation and make a bond with it to form our final product, Y and E, both joined onto our original alkene, which now has a single bond between the two carbons. So let's look at some specifics. The first one we'll look at is the reaction of an alkene with hydrogen bromide, and we end up with the single bonds, bromine adding on one side and hydrogen adding on the other. And the conditions to generate the hydrogen bromide, we would use sodium bromide solid and concentrated sulfuric acid as an oxidizing agent, and heat it up. So if we have a look at the mechanism, hydrogen bromide is a polarized molecule, the hydrogen being the electrophilic part. So if we have the pi bond reacting here, we get our carbocation intermediate here, fill in the hydrogens, and of course as a result of this bonds breaking here, we end up with Br minus. And then the last step, the bromide ion joins on there to make our final product. And all the hydrogens, and now the bromide, or the bromine. So let's look at another reaction, and that is with concentrated sulfuric acid. We don't have to heat this up, we can just react this cold, and we will get an alkyl hydrogen sulfate where we've added all but one of the hydrogens from the sulfuric acid onto the molecule, or the hydrogen has been added here. This is a very useful intermediate stage, because then if we add some water to this and warm it, we can flush the acid part of the molecule off to leave behind an OH group. In other words, this gives us a way of making alcohols from an alkene. So as I said, the first condition is cold concentrated H2SO4 sulfuric acid. We don't have to heat that up. And in the next step, to get the alcohol, we add water and we heat it. Now let's have a look at the mechanism. Okay, so here's our sulfuric acid. This hydrogen's very electropositive. It's very acidic, this part being delta minus. So here we have the electrons in the pi bond making a bond with the hydrogen, and of course this one breaking to give us our carbocation intermediate. And of course we have here our hydrogen sulfate ion, which this negative charge here in the oxygen looks to make a bond with the carbocation to give us our next product, alkyl hydrogen sulfate. And the last step for this, having now done the electrophilic addition, is the water and heat to give us our final product, which is the alcohol. Of course, the test with bromine wouldn't be complete if we didn't discuss this, because this is the chemical test for a carbon-carbon double bond, or even a carbon-carbon triple bond, if we're talking about alkanes, which react in a very similar way. So here is a straightforward reactor with bromine, and we end up with bromine adding across the double bond to give us a dihalogenal alkane. That is two halogens attached to an alkane. And we can use bromine liquid for this, or aqueous bromine, bromine water. Normal laboratory conditions, we don't have to heat it up, we just shake it up. And as I said, this is a chemical test for alkanes, so it changes from brown to colourless, not clear, colourless, no colour. Now if we think of the mechanism here, we kind of run into problems, because the bromine-bromine bond is a true covalent bond, it's not polar at all. So we have to ask ourselves, where is the electrophile when we're talking about bromine? It's not obvious. And the answer to this question is that the pi bond induces the polarization in the bromine molecule. In other words, the pi bond creates its own electrophile from the bromine in order to react. So in other words, if we represent the pi cloud showing this big concentration of negative charge and the covalent bond with the bromine as a dot cross diagram, what happens as the bromine molecule approaches the pi system, there's a repulsive force experienced here, which kind of pushes these electrons towards this second bromine. In other words, as a result of this induced repulsion, we have a concentration of negative charge on this bromine, and this one becomes electropositive since its electron has moved away from it. And this is where our electrophile has been generated by interaction with the pi system. So this now allows us to draw the mechanism. The pi system now bonds with this electrophilic bromine, and this bromine here will take both of those electrons, and again we get our carbocation intermediate. And of course, now having generated our bromide ion, this reaction can then continue on to make our dihalogenal alkane that we had at the beginning. Now notice that all of the examples here have used a symmetrical alkene. We've used ethene for this, and these are true for all symmetrical alkenes. However, if the alkene is not symmetrical, if it has some different groups on the two carbons that have the double bond, then we have to have further consideration. There are complications to add on to that, and to find out what happens in those cases and explain them, check the Show Me on the Markovnikov addition to Alkenes.